Hi, my name is Charlotte, and I'm going to answer another math problem from my friend Holly in preparing for the GRE. This is actually a really good problem, and I know that makes me a huge math nerd, but I was a math teacher, so we already knew that. So here's the problem, and I'm going to write upside down again, so I hope that this is legible. But it says, if the distance from A to B equals the distance from B to C equals the distance from C to D, and triangle CDE has an area of 42, what is the area of triangle ADG? And I've copied the figure here. So, like I said, this is a really great problem because it actually draws on a whole lot of stuff. So, let me tell you the kind of the fool's way of answering this, and then the right way. So first of all, I'm a math nerd, so the first thing I'm going to do is make my little hash marks. Oops, that's the wrong side of the triangle. Here, here, and here. So you're sort of the person who doesn't think this problem through is going to think, well, that means that basically this shaded in triangle is, since the hypotenuse is 1/3 the hypotenuse of the larger triangle, then I need to triple the area of the triangle to get the area of the full triangle. And that would be a great way to do it, except it's not right. So, here's how you would do it. So the first thing that you need to recognize, and this sounds a little arbitrary, but it actually is pretty important, is that these hypotenuses, or little chunks of the larger triangle's hypotenuse, being equal, means that these nested triangles are similar. And I'll show you why. It's because remember that the properties of angles say that alternate interior angles are equal. So that's like if you have two parallel lines intersected by a transversal, then all of the vertical angles are equal, but also the alternate interior angles, so like this one and this one, are equal. And then also the corresponding angles, so this one and this one would be corresponding, those two. So we're going to use this property right here, but the first thing is, well, it has to be two parallel lines intersected by a transversal. So do we have that? Well, actually, we do. And we only can say that because it's a right triangle. If it weren't a right triangle, you actually can't use these properties. You have to have a right triangle in order to do this, because with it being a right triangle, then you can say with certainty that these two lines are parallel, because that's the only way you can have two right angles. They have to be parallel, which means basically this little guy, for instance, is acting as a transversal, which means we can say that this angle and this angle are equal, which means this one is 2, or I should say congruent, or equal, either way. Okay, so if you have two equal angles of a triangle, then that means the third is congruent also. And really it doesn't even matter in this case because they actually all share the same third angle. And now, drum roll please, if you have angle, side, angle, that's a similarity rule for triangles. So since each of these three triangles have, well actually angle, angle, angle is one also. So either way, we can say with certainty that these triangles are similar. CDE, BDF, and ADG are all similar. Now we can kind of move forward. So because they're similar, then we can also assume that DE is similar to, and notice it's not equal to, it's similar to DF, which is the kind of upstanding side of this middle triangle, which is similar to DG. So the reason that helps us is because we know that line DG is 3 times as long. And the reason we can say that is because in a similar figures, for instance, DA and DC, since this little triangle is similar to the bigger triangle, because they told us that these little segments here are equal, then that means we know that this hypotenuse is 1/3 of the largest hypotenuse. Well, the thing with similar figures is that whatever is the multiplying ratio for the segments is the same ratio for all of the segments, which means that the ratio between these sides is also going to be that the smallest is a third of the largest. So that means DE, the length from D to E, is equal to 1/3 of the length from D to G. Or if you want to say that backwards, you could say that 3 DEs make up 1 DG. Okay, so I know I'm getting long-winded here, but I'm going to wrap it up. So once you realize that basically if you can multiply this little guy right here by 3 to get the largest triangle, and that also implies, by the way, that the bottom of the little triangle is also 1/3 of the bottom of the larger triangle, because again, whatever relates two of the sides relates to all the other sides. So once you have that in your head, then you can go, oh, okay, so what is the formula for the area of a triangle? Well, it's 1/2 the base times the height, right? Well, let's just say, in a sort of a thought experiment, we're going to triple the base and triple the height. So we're going to basically do 1/2 times 3 bases times 3 heights. Because again, we're taking this little base and multiplying it by 3, taking this little height and multiplying it by 3. So what happens to the area? Well, you basically get 1/2 times 9 times base times height. Oh, sorry. All right, well, check it out. The original formula for area of a triangle is just 1/2 times base times height, which in the case of this little triangle up here gave us 42. So this piece is equal to 42. Well, here we have that piece, 1/2 times base times height. So this part is 42. So all you have to do is multiply 42 times 9, because here's that 9 where it falls out, which is equal to 378. So the area of the largest triangle is going to be 378. So just to recap, and this is actually, a lot of times they'll give you problems like this without drawing you a picture. And so if you take, for instance, the length, or let's say the dimensions of a two-dimensional figure, like a square, or let's just call this a rectangle. Okay? So if you have length x and width y, and remember, they don't have to give you a picture in order to ask you this question. But if they say, if you multiply the dimensions of a rectangle by 5, how will the area change? That's actually a really common question. So if you multiply x and you multiply y times 5, what will change about the area? Well, again, the poor man is going to say, oh, well, you multiply the area by 5 because they're going to be similar figures, right? And that's kind of the trick. Well, it's not just that, because here you can clearly see when you multiply each dimension, it kind of gets counted twice in the case of a two-dimensional figure. So that means it's actually going to be 25 times xy. If, though, they ask you about, let's say, a rectangular prism. Oops, I just connected those completely wrong. And they say, if you multiply the dimensions of a rectangular prism by 4, what will be the resulting change in volume? Well, here again, you have 3 pieces that go into this. You would multiply the length times the width times the height. I think I just wrote that wrong. There we go. So when you change each of these, like put a number in front of each of these, like say, what did I just say, triple? So that would mean you would get a 3 here, and a 3 there, and a 3 there. So you would actually get 27 times the regular volume, which is just xyz. So those problems are really clever, and just as a final note, I'll show you a quick way to remember, like just kind of the shortcut. Remember that area is always given in however many units, whatever the units are, squared, right? And volume is always given in whatever units cubed, like cubic feet or whatever. Well, this is a good way to remember, because basically whatever the multiplying factor or the ratio, so in this case it was 3, and in this case over here it was 5, whatever the ratio is, that's how many times, because that's how many dimensions it's going to go into it, is the exponent. So if you're dealing with area, you basically take the ratio and square it, and that's going to be the difference in area. If you're dealing with a problem that involves volume, you're going to take the ratio, like 5 or like 3, and you're going to cube it. And that's going to be the difference in the volume. Okay? By the way, don't forget that surface area is just more area. It works the exact same way. So if, for instance, you said even about a 3-dimensional figure, and this is where they can really trip you up, because a lot of people memorize this rule, but they don't really know where it comes from. But if I said about this same rectangular prism, if I multiplied all the dimensions by 3, what would be the difference in, or what would be the change to the surface area? Well, most people, if they are a little bit savvy with these rules, might say, again, it's going to change by 27 because you're multiplying all 3 dimensions. Yes, but remember that the surface area of a rectangular prism is just a whole bunch of rectangles added together. It's just a whole bunch of areas of rectangles, like this rectangle, and the one back here, and the one on the back, and the one on the side, and the one on the bottom. It's just all those added together. So it's just a whole bunch of cases of this, which means that you do the same thing, actually. So surface area, also, you just square the ratio. So if I said, if you multiply all the dimensions by 4, what would be the resultant change in surface area? It would be 4 squared, which means 16. So it would be 16 times larger in surface area. Okay? So I hope that helps. Again, the biggest trick with this triangle one, and this is really a trick because they will be kind of jerkbags about this, is that unless you have that these are right triangles, you cannot assume that these triangles are similar. And that seems like a small deal, but it's actually a really big deal, because all they would have to do is not put those squares in. They don't have to tell you, note this is not a right triangle. They just know that people will assume it is. If it's not a right triangle, this problem is not solvable, because you don't know that these are similar triangles. Having these little tick marks here, which is all that they give you in the problem, is not enough without knowing that these were parallel lines. Because otherwise you can't assume they're similar, which means that the gap between here and here is not knowable. Okay? So always look for that. It's like 30, 60, 90 triangles. Everybody wants to use that trick when there's no 90 degree given. Don't make that mistake. Don't assume that it looks like it, because even if it's 29.99, it's not a 30, 60, 90. So the rule doesn't work. All right, so I hope that works. Holly, let me know if you have any more questions, and I will get right on it.